Today we will finish up chapter 4. That's the first thing we'll do. So I will do more problems. And then I get into foundations for trigonometry. Now, there are some parts in our textbook that you can start reading on your own. Read section 5.1, and I will go over that tomorrow. Okay, but what I will do today, basically most of them, actually 5.2, most of 5.2, and tomorrow we will do, we'll do 5.1, finish up 5.2, and then go to 5.3. And then I think we can do 5.4 maybe, but we'll see later. Yeah, but we'll see later. Okay, but the main point today is to lay down a solid foundation for the trigonometry that we'll do basically solidly tomorrow. Okay, now let's go back to 4.6. Last Thursday, we did some questions. I think only 1 or 2 questions from 4.6, but those are the one we really need from exponential equation. Let's go on to some logarithmic equation. For example, we do number 20. So I think I will spend the next 45 minutes in working on 4.6. Maybe number 20, solve log base, so no base, so that's base 10, 5x plus 1 equals to 2 plus log of 2x minus 3. Again, just like before, we will put the log together on one side, and the plan is we'll put the log into single log. So this is log, difference of logs is log of quotient. And then because the base is base 10, so I change this into exponential form. That's 10 squared, which is 100. So this will be 5x plus 1 equals to 100 times 2x minus 3, 200x minus 300. That's 301 on the other side, and this side is 195. Okay, so x equals to 301 over 195. You can just leave it like that. Of course, if possible, reduce it. And if you use calculator, make sure you round it to 5 decimal places. Only round your final answer to 5 decimal places. This will be 1.54359. Now, before we let go of this problem, make sure you check if this x will make the argument becomes positive. Now, this is positive times 5 plus 1, that will be positive. That's easy. Okay. Now, this guy multiplied by 2 is more than 3. More than 3 minus 3 is more than 0. So we are fine. Okay, that's for number 20. Now let's see the harder one, number 22. So in this section, we don't expect the solution to be a nice number. Solve log x plus 3 plus log x minus 3 equals to log x squared plus 5 minus 2. Okay, let's put them together on one side. Log x plus 3 plus log x minus 3 minus log x squared plus 5 equals to -2. Make it a single log on one side. That would be x plus 3 x minus 3 over x squared minus plus 5. That's equals to -2. This is log of x squared minus 9 over x squared plus 5 equals to -2. So change it into exponential form. X squared minus 9 over x squared plus 5 equals to 10 to the -2. That's 1 over 10 squared, 1 over 100. So cross multiply, I will get 100 times x squared minus 9 equals to x squared plus 5. What is this? This is 100 x squared minus 900 equals to x squared plus 5. So 99 x squared equals to 905. Okay, so x squared equals to 905 over 99. So x equals to plus minus square root of 905 over 99. Okay, so there are two solutions here. The positive branch, I think when you put it in, the positive branch is okay. Right? The negative branch will not be okay. Because it's when you plug that in, you get negative number. You get negative argument. So let's see. So that's 905 divided by 99. When I do the square root, I get 3.02348. And this is negative 3.02348. We have problem here. When you plug that negative number into this, or sorry, not that one, the original question, into this or into this, it will not be okay. Okay, so cross it out and underline the one that is the solution. Okay, that's for number 22. Let's do one more like this, question like this. Number 24. So number 22, we have two solutions. One of them doesn't work. Number 24, we have solve log base 10 again, x minus 4 minus log 3x minus 10 equals to log 1 over x. On the left hand side, we get log, difference of logs is for log of quotient. And log blah equals log blade implies blah equals blade. Then from here we cross multiply by the LCD, right? If you think about it, if I multiply by the LCD, multiply by x, 3x times 10, then you will see that's basically cross multiplying. In this case, it's x squared minus 4x equals to 3x minus 10. So x squared minus 7x plus 10 equals to 0. Now I plug that I factor x minus 5, x minus 2 equals 0. So x equals to 5, x equals to 2. When x equals to 5, this is positive 1, this is positive 5, and this is still positive. So that guy is okay. This guy is okay. How about when x equals to 2? When x equals to 2, it's not okay here. Right? It's not okay there. So I cross it out. Okay. I hope you see the pattern. It's actually not too hard to do. Number 26. Number 26. We have 3 times of 3 times 3 to the x plus 9 times 3 to the negative x equals to 28. This is like 3 times 3 to the x plus 9 times 3 to the x on the denominator, 9 over 3 to the x on the denominator, and then equals to 28. That's what 3 to the negative x means. Then I will multiply by the LCD, multiplied by 3 to the x. Then I get 3 times 3 to the x squared plus 9 equals to 28 times 3 to the x. Now I want you to realize that this becomes a quadratic-like equation that we learned before. This is 3 to the x, not 3x, by the way. This is 3 to the x, my x should be out. Minus 28 times 3 to the x plus 9 equals 0. See, if I say let u equals to 3 to the x, then I get 3u squared minus 28u plus 9 equals 0. Okay, and then we try to factor it. Take 3u, u minus 9, this is u minus 1 equals 0. So u equals to 1/3 or u equals to 9. But u is 3 to the x. So this is 3 to the x equals to 3 to the negative 1 by 1 to 1ness, x equals to negative 1. And because this is exponential function, you see the u is 3 to the x, right? So x can be anything. The domain of exponential function is all real numbers. This is 3 to the x equals to 3 squared, so x equals to 2. Both of them are okay. Now, using the same line of thought, we will do number 28, but you will see number 28 is messier because it's not factorable. Number 28, solve this exponential function 2 to the x minus 6 times 2 to the negative x equals to 6. Oh, by the way, before I forget this, I want you to realize that this part here may be sneakily written as 3 to the x plus 1. And this part here may be sneakily written as 3 to the negative x plus 2. Okay, so imagine if they ask you this question, 3 to the x plus 1 plus 3 to the negative x plus 2 equals to 28. So you basically need to rewrite that, rewrite this term here and then rewrite this term first. Okay. Now let me go back number 28. This is 2x minus 6 over 2 to the x equals to 6. Multiplied by the LCD 2 to the x. It gives me 2 to the x squared minus 6 equals to 6 times 2 to the x. That's 2 to the x being squared minus 6 times 2 to the x minus 6 equals 0. Okay, now then I see that this is a quadratic-like equation. I let u equals to 2 to the x such that the equation becomes u squared minus 6u minus 6 equals to 0. Oh, I can use completing the square. I need to add 9 to both sides, right? Negative 6 divided by 2 is negative 3. Negative 3 being squared is 9. That's the number of that. Negative 3 being squared is 9. That's how I know. That's how we know we will add 9 to both sides. So this is u minus 3 squared equals to 15. So u minus 3 is plus minus square root of 15. U equals to 3 plus minus square root of 15. Now, so there are two solutions. The first one is 3 plus square root of 15. The second one is 3 minus square root of 15. Now, it's 2 to the x though. So to solve this, I rewrite it into log form. Okay, so this is log base 2 of 3 plus radical 15 equals to x. That's the exact form. And if you want to write it in using approximation, let's change the base first. I will change it to base 10. But you can also change it to base e if you like. And that will give us remember that the domain of log is positive, so the argument here has to be positive. This has to be positive. Okay, so log 3 plus square root of 15 divided by log 2. I get x equals to 2.78094. Okay, that's for the first part. Now the second part, 2 to the x equals to 3 minus square root of 15. But the thing is, 3 is less than square root of 15. Yeah, 3 is square root of 9, right? The square root of 9 minus square root of 15 will be negative. But the range of 2 to the x is from 0 to infinity. So no solution because the range of 2 to the x is positive real number. Okay, so here we have only one solution. Sometimes if you wonder, Thomas, how do I know? I need to check. Well, keep in mind with the domain, keep in mind with the domain of those functions we are dealing with, and in this case is the range. Okay, so I have solved some common type of questions in exponential and logarithmic form. Now we go on to the one that more into using the property. Okay, so the followings will be quite fast to use, to do. Log square root of 10, square root of x equals to square root of log x. How do we solve this? Now this is not log blah equals log b. This is not log blah equals log b style. No, it's not. So we can't just cancel the log. We can't just cancel the log. Let's do some manipulation using the property. This is log to the power log x to the power of 1/2, right? And this is square root of log x, right? And that's property number 3. And then I'm sorry, that's property. Yeah, that's property number. That's just square root of x. And then using property number 3, I bring the 1/2 to the front. Now from here, you can actually use substitution. You see that log x appears on both sides, right? So you can say, we can say, but you don't have to. I think this is quite simple to do without substitution. So we have 1/2 u equals to square root of u. When we square both sides, the other side we have u. Now, remember, once we square both sides, we need to check whatever answer we have in our final answer against the original equation. This will be 1/4 u squared equals to u. So u squared equals to 4u. Now, don't divide by u. Don't divide by u. Why not? Because what if u equals to 0? The proper way to do it is to factor. Okay. So we get u equals to 0 or u equals to 4. Now you put it back. That's log of x equals to 0. If log x equals to 0, then x equals to 10 to the 0, right? Which is 1. And then for the other branch, log x equals to 4 in exponential form. Log x equals to 10 to the 4 or 10,000. Okay. You will see this question is actually quite similar to question number 34. Question number 34, it's quite similar. It's not exactly the same, but quite similar. We have log x cubed equals to log x being cubed. You will see I bring the 3 to the front. 3 log x equals to log x being cubed. And then I do substitution, let u equals to log x. Then I get 3u equals to u cubed. That's a polynomial degree of 3, and I believe we can factor this. Let's set one side is 0, u times u squared minus 3. So either u equals to 0 or u squared minus 3 equals to 0, or u squared equals to 3, u equals to plus minus radical 3. So the solutions for now is u equals to 0, u equals to radical 3, u equals to negative radical 3. Now then you put it back. This is log x equals to 0. X equals to 10 to the 1, 10 to the 0, which is 1. This guy here will be 10 to the radical 3. And this will be 10 to the negative radical 3. Okay. Now, when you have the answers like this, always write the exact solution first and go on to approximate solution. You use calculator if I ask you to get the approximate. But if I don't ask you what the solution is supposed to be, then always assume it is in exact form. Let me write it down. If I don't ask for approximate form, then you need the exact form. Even if I do, you still need the exact form first. Okay, hold that a big note. So in any way, you always give me the exact form first. I will do one more problem from here. And then I go on to chapter 5. Now the next one problem is actually quite unique, and I strongly recommend you to work on this problem later on. I usually ask this in my test. Okay, let's say I pick question number 46. Y equals to solve for x. Y equals to e to the x minus e to the negative x over e to the x plus e to the negative x. Now you will see if we see this as a function, this function is actually one-to-one, and therefore we can find the inverse function. Okay, we will see that this function is actually one-to-one, and therefore we can find the inverse function. But let's say we want to solve for x first. So basically, we want to solve this such that we get x equals something. Okay, we want to have x equals something. How do we do that? The solution, multiply by the LCD, right? Y, let me write down the question first. Multiply by the LCD, y times e to the x plus e to the negative x equals to e to the x minus e to the negative x. It's y e to the x plus y e to the negative x e to the x minus e to the negative x. Now, I don't like the negative exponent. Let me make it into over e to the x. So this is plus y over e to the x equals to e to the x minus 1 over e to the x. Now it is clear that we will need to multiply by the LCD e to the x first. The nice thing about e to the x is it will never be 0. So up to this point, we don't have any x that we need to avoid. We don't have any x that we need to avoid. Now when I multiply by e to the x, then I get y e to the x times e to the x, that's squared, plus y equals to e to the x being squared minus 1. But e to the x being squared is e to the 2x. Now remember, the goal is we need to solve for x, right? So what we plan to do is to have x terms on one side and those without x terms on the other side. Okay, will factor e to the 2x, so I get y minus 1 here. So e to the 2x equals to negative y minus 1 over y minus 1. I can actually factor the negative on the top, right? So if I factor the negative at the bottom, it becomes 1 minus 1. Okay. So e to the 2x now can be written as 1 plus y over 1 minus 1. Are you with me? And therefore, 2x equals to natural log of 1 plus y over 1 minus y. X equals to 1 half natural log of 1 plus y over 1 minus y. Now notice that the reason I go over this problem is because the function that you deal with here in calculus 2 has something to do with hyperbolic tangent. We have not learned trigonometry yet. We will do very, very soon. But this is even the next level. You will see, even if you see this, it will be in calculus 2. Yeah, even if you see this, it will be in calculus 2. Now, so suppose, let me kind of like continue with this question. In fact, if I call this let fx equals to e to the x minus e to the negative x over e to the x plus e to the negative x. Now then, notice that the first possible question is to find the domain. Find the domain. But you will see the domain depends on the denominator cannot be 0, right? Okay, the denominator cannot be 0. But you see e to the x plus e to the negative x, both of them non-negative. Right? So when you add them, it will still be non-negative in any x. So the domain will be all real numbers. Right? But the second question is the hard one. Find the range. And for us to find the range, we actually look at the inverse first. Okay? When we get the range, to find the range, you notice that x equals to, get x equals to 1/2 natural log of 1 plus y over 1 minus y. Right? Now, for this to work, then the argument has to be strictly positive. The argument has to be strictly positive. 1 plus y over 1 minus y has to be strictly positive. Okay? And then we get the critical numbers are y equals to -1, y equals to 1. The sine graph, -1, 1. This is undefined here. This is 0 here. Will be when x equals to 0, that's positive. So this is positive, negative, positive. Now that's negative here. So you need that to be strictly positive. So it will be from -1 to 1 only. So the range will be from -1 to 1. Now let's take a look on what the graph actually looked like. Out of curiosity, so let's see a new sharing here. We have y equals to e to the x minus e to the negative x divided by e to the x plus e to the negative x. See, that's what it looks like. Okay, here, and then copy paste that for our note. So you see the function is actually one-to-one function. Right? It's one-to-one function. Okay, and the question solving for x in this equation here has the far-reaching consequence that is basically finding the inverse function, maybe if the function is one-to-one. If not, it is still the inverse, it's just not a function. But then we don't need to get to step 4 of inverse function to find the range, right? So even if the inverse is not a function, we still can use that to find the range. Now we have that technique even in our test 2, and don't forget we still have that technique in future. Okay, now this is the finishing up of 4.6. Your suggested homework from here will be let me just give you 4.6 as a whole. 4.6, I want you to do from number 1 to number 45. Do the odd ones. And start working on this though. If you really want to be successful on this section, on this chapter, make sure you summarize that this section with this 4.6 well. Okay, that's for this 4.6. We will go on to the chapter 5, trigonometry part. Instead of going over 5.2, instead of saying that we go over 5.2, I would just call that an intro. Intro to trigonometry, because there are some foundations I need you to remind yourself. Now the thing is trigonometry at SMC, pre-calculus at SMC requires Math 2 requires foundation in Math 20, which is intermediate algebra or algebra 2 in high school. Actually, foundation in, and Math, I think that's Math 21 or 32. Math 32, that's geometry in high school. Now, at SMC, Math 32 already has trigonometry, basic trigonometry. Which you can say things I do basically today. Okay, which basically what I do today. Now, what are those 3 foundations? The first one, Pythagorean Theorem, which at this point you should already get really good. Pythagorean Theorem, but I will review that again. But one of the consequences of Pythagorean Theorem I want to mention is something called Pythagorean triplet. Second, right triangle definition of trig functions and then values of trig functions on special angles. Okay, now if we have a chance, I think we do, then we will learn how to use calculator to compute those trig functions. Okay, but let's start with one, the easy one first, Pythagorean theorem. Pythagorean theorem, we know that I'm supposed to have sine. Okay, so suppose I have a right triangle. Suppose I have a right triangle and right angle here. Let's say triangle ABC with right triangle at C. Okay, the way we name the vertices using capital letters, and the sides has two ways to name it. The first way to name the sides, by the way, this is something we learned in geometry though. The way we name the sides is like this segment here, we call it segment BC. Okay, that's segment BC. Or we also use lowercase a. Now, segment BC is simply because if you have a segment with endpoints B and C, you can call that segment BC. Okay, but from triangle point of view, this side here, this side here is the side opposite of angle A, opposite of vertex A. So this side is named after that vertex, but using lowercase. Okay, so capital A refers to the vertex, lowercase a refers to the side opposite of that vertex. Okay, now we tend to use A especially for if we want to say the length. Now this guy here, this is side AB, also called C. This is side AC, also called lowercase b. Now, the legs of a right triangle are the side whose one endpoint is the vertex with right angle. So when we say the legs, it refers to this guy here and this guy. These two things are the legs. Okay, we can say because the hypotenuse will be the longest side, then the legs of right triangles also the shorter two sides of the right triangle. Okay, we can also say, but I prefer to say the legs of a right triangle are the sides that is adjacent to the right angle. Okay, not opposite of that right angle, but adjacent to the right angle. Now, then by Pythagorean theorem, we have learned that Pythagorean theorem says that the sum of the squares of the legs of a right triangle, in the right triangle, the sum of the squares of the leg equals to the square of the hypotenuse. We learned that before. Okay, we learned that before. In fact, in geometry, we even have something stronger, that any triangles whose sides satisfy Pythagorean theorem must be a right triangle. So this result is actually very strong. Pythagorean theorem applies not only that Pythagorean theorem applies for the right triangle, but if Pythagorean theorem applies, it must be a right triangle. I'm saying this. What we have learned before, we are having that once we have right triangle, then you can apply Pythagorean theorem. Right? That's what you know before. But from geometry, we learned that once Pythagorean theorem applies, it must be a right triangle. So that's if and only if case. Okay? Now let's say, for example, if I have a right triangle, let's say if I have a right triangle, let's say the right angle always at C. If I don't say anything, then right angle always at C. And suppose the hypotenuse is 8 and one of the leg is, let's say, 6. Then find the other leg. The name of the other leg here is B. Okay, find the length of the other leg, B. Solution. We use Pythagorean theorem. This is 6, this is B. This is 6 here. This is 6. So 6 squared plus B squared equals to 8 squared. 36 plus B squared equals to 64. B squared is 64 minus 36. I think that's 28. So B squared is 28. So B is square root of 28. Supposed to be plus minus, but this is the length. So I just take the positive branch. And if you have this, you can simplify this. This is 4 times 7, right? So B is 2 square root of 7. Okay, that's one application of Pythagorean theorem. That's one application of Pythagorean theorem. I think that part is easy. Now, how about Pythagorean triples? Pythagorean triples. Triples A, B, C. A triple A, B, C where A, B, and C are all integers. And of course, it has to be positive integers. Okay. Is a Pythagorean triple. Pythagorean triple. If it satisfies Pythagorean equation, Pythagorean theorem. Pythagorean theorem, A squared plus B squared equals to C squared. Now, of course, the C squared, the C here will be the largest number. Okay, the C is the largest number. And we know that actually again from trigonometry that the hypotenuse is always the longest. Okay, the hypotenuse is always the longest. The hypotenuse is always the longest of these three sides. Okay. One triple, for example, we know that 3 squared plus 4 squared equals to 5 squared. So the triple is 3, 4, 5, where 5 is the hypotenuse. Another one, it's 5 squared plus 12 squared equals to 30 squared. Now I write this down so that you memorize, and we use these numbers a lot actually. So you can imagine if I have, this is 5, this is 12, this is 13. The others, we have 7 squared plus 24 squared equals to 25 squared. So 7, 24, 25 is a triple. I think there's another one. Hold on. 8 squared plus step. 15 and 17. So 8, 15, 17 is also a triple. Okay. Now, if ABC is a triple, is a Pythagorean triple, then all its multiple are also triples. So because, for example, 3, 4, 5 is a triple, then if you double it, 6, 8, 10 is also a triple. Okay. If you multiply by 10, it's also a triple, or you multiply by 100, also a triple. Or even you make it, let's say you divide by 2, that's also a triple. Okay, now that's the good thing about these Pythagorean triplets. And the thing is, the reason I tell you this because they show up a lot in trigonometry. So it'll be nice if you can memorize this Pythagorean triple. Okay, the one here, the one here, the one here. Memorize this as a triple. And remember, the largest number has to be on the hypotenuse. Okay, the largest number has to be on the hypotenuse. So suppose I have this. Suppose I have 10 here and then 6 here. Then I know this must be 8. Okay, because 10 and 6 is double of this, 10 and 6. So the other one must be 8. Of course, you can always do it by hand, apply that into Pythagorean theorem, and get that 8 slowly. Okay, but again, because we see it too often, it will be better if we just memorize them. Now, right now it's 12:05. Let's take a break. We come back at 12:15. Okay, let's continue. We are done with the Pythagorean theorem and especially Pythagorean triplets. Memorize this, please. Okay, memorize these triples. They usually show up in this, how to say that? The order of frequency. Like the first one is showing up a lot, and this is the second most often, third and fourth most often for integers. Okay. Now, of course, we may have ugly case like the one we had earlier here, in which one of the side turns out to be not rational, not a rational number. In this case, it's irrational. Okay, but for the rational numbers, actually comes from integers. Okay, comes from integers, and the one most frequently show up are these 4. Now, once we get the Pythagorean triples and Pythagorean Pythagorean theorem and Pythagorean triples, then we can go on to the second part. The second part will be on definitions of Pythagorean function, trigonometric function on the right triangle. Definition of trig functions on the right triangle. Now, Pythagorean functions actually applies not only for right triangle, but we will start from a right triangle situation. Suppose I have a right triangle here. Okay. And let's say the angle is this angle here on this side, from this vertex. Let's say that's the angle. I call that angle theta. It's a Greek letter theta. Now, if that's angle theta, the side opposite to that angle theta is called the opposite side. Okay, now the side adjacent to that, the leg that is adjacent to that angle but not hypotenuse is called adjacent. And just like before, this is the hypotenuse. Now, sine theta, denoted by sine theta, is defined to be, in a right triangle again, it has to start from a right triangle. Okay, is defined to be the opposite over the hypotenuse. Cosine theta, denoted by cos, cos theta. So even though we write cos theta, we still read it as cosine theta, is the adjacent over the hypotenuse. Tangent theta is denoted by tan theta is opposite over adjacent. These three are the primary trig functions. There are three more. Secant, cosecant, and cotangent. I'll write it below it. Secant theta, denoted by SEC theta, is, you will see this is actually the reciprocal of cosine. So hypotenuse over adjacent. So consequently, let me use red color. So secant theta is actually the reciprocal of cosine theta. Cosecant theta, denoted by CSC theta, is the reciprocal of the sine, which is hypotenuse over the opposite. Cosecant theta is the reciprocal of sine theta. And finally, cotangent theta, denoted by COT theta, is the reciprocal of tangent, that's adjacent over the opposite. Now, I call this second group here the secondary trig functions because we don't really talk about that. We do, but not that much. Okay, compared to the sine, cosine, and tangent. The amount of work we apply to sine, cosine, tangent is at least 20 to even 30 times more than secant, cosecant, and cotangent. So if there's anything you need to memorize today, which I do assume you have memorized that in the past, you must have seen that in the past. But in case you forget, right? In case you forget these three, then at least memorize the first three first, okay? Memorize the first three first, get really, really good with that. Then you go on with the secant, cosecant, cotangent, okay? Even though you have learned this before, I don't expect that you memorize all of them. So today we are still basically going through the phase of recalling, okay? Refreshing our mind about these trig functions and the definitions. Okay, now tomorrow, I already assume you study from what we have today. Okay? Now, let's apply that. Let's say, for example, we have a right triangle. For example, let triangle ABC be a right triangle with right angle at C. And A equals to, let's say, 5, B equals to 7. Find all trig values for angle A. Now, word problems in trigonometry, translate that into graph first. So sketch the graph. It will be nice if you do, right? Remember, you say that you're a visual learner, right? Everybody is actually, but not everybody wants to graph it themselves. No, you should change. Okay, you should graph it. Okay, so A, B, C. C is the right angle. Side A is 5. Now remember, side A is opposite of vertex A. So this is 5. Side B, that's the side opposite of vertex B, is 7. So let's find that C first. Okay, we want to find that C. So solution: A squared plus B squared equals to C squared. 5 squared plus 7 squared equals to C squared. 25 plus 49 equals to C squared. What's that? 60, 74, huh? 74 equals to C squared. So C is square root of 74. I don't think I can simplify that. That's the simplest possible. Now, then find all trig values for angle A. So basically the question is, what is sine of A? What is cosine of A? What is tangent of A? What is secant of A? What is cosecant of A? And what is cotangent of A? We need to answer all those 6. Now memorize the first 3 first. Memorize the first 3. Sine A will be opposite over hypotenuse, square root of 74. Oh, but we don't want the radical at the bottom. Multiply the top and the bottom by radical 74. This is what we get. Cosine A will be 7 over square root of 74. Right, multiplied by the rational is the denominator, so I get 7 square root of 74 over 74. Now tangent A is opposite over adjacent. Oh, we are done. Secant A is the reciprocal of cosine. Actually, you can just memorize it that way. Secant is the reciprocal of cosine, while cosecant is the reciprocal of sine. And cotangent is the reciprocal of tangent. That's it, we are done. Okay. Now, let's do a problem from our textbook. I think this problem is on the easy side. Should be. This problem is on the easy side. Let's say we take number 6. Number 6. In our textbook, that's page 346. Number 6, we have a picture, looks like this. And then we have theta here. This is 3, this is 1. Okay, let's call this A. So A squared plus B squared equals C squared. A squared plus 1 squared equals to 3 squared. A squared plus 1 is 9. So A squared is 8. A is square root of 8, which is 2 square root of 2. So that is equal to 2 square root of 2. Okay, now pay attention that your theta is now here. Okay, that's your theta. So sine theta will be the opposite of that theta is 2 square root of 2 over 3, the hypotenuse. Cosine theta will be the adjacent of that theta, that's 1 over the hypotenuse. Tangent theta will be opposite over adjacent, or simply 2 radical 2. Secant theta, the reciprocal of cosine, that's 3 over 1, or simply 3. Cosecant theta is reciprocal of sine. Let me rationalize the denominator. And cotangent theta is 1 over 2 radical 2. That's radical 2 over 4. Okay. Then let's go on further. Suppose we do number 8. It's more abstract situation. Number 8, we have this graph here. And the theta is here. They don't give us number. They only give us this is C and this is A. So what will our B be? So our B will be A squared plus B squared equals to C squared. So B squared equals to C squared minus A squared. B will be supposed to be plus minus square root, but because that's the length, we just get the positive fraction. Now this is theta here. Then what is sine theta? Sine theta will be the opposite, which is square root of C squared minus A squared over hypotenuse C. Cosine theta is simple A over C. and tangent theta will be opposite over adjacent. Okay, and then secant theta, that's reciprocal of cosine. Cosecant theta is the reciprocal of sine. And then cotangent theta is the reciprocal of tangent. Okay, and then from there you can rationalize your denominator. But some warning though, warning. Maybe I need to write this down. I don't expect you to make this mistake, but just in case. Warning. Square root of c squared minus a squared is not equal to c minus a. No, it's not. It's not. Okay, and you can try using c and a equals to 5 and 4, let's say. Then you will see one of them give you 3 and the other one give you 1. So square root of difference is not difference of square root. No, it's not. Okay, square root of difference is not square root of difference is not difference of square root. Now, now we will go backward. The following technique seems to be strange. It's slightly different from our textbook. But I want to build your intuition first. Suppose, for example, let theta be an acute angle. Now, from your reading in 5.1, later on, you will see theta is an acute angle means theta is between 0 degree to 90 degree. And because theta is an acute angle, it means we can put that into a right triangle. Okay, let's say this is my theta. Let theta be an acute angle and, for example, number 18. So our sample number 18, they tell us that cosine theta is 8 over 17. Cosine theta is 8 over 17. Now, in that right triangle with angle theta, cosine is 8 over 17. Then I can plug this. Adjacent is 8, hypotenuse is 17. Okay, that will give us cosine theta 8 over 17. Now, by Pythagorean triple, the other side is you can apply Pythagorean theorem, okay? But if you happen to memorize Pythagorean triple, then you will see this is actually 15. Now the question is, if you know cosine theta equals to 8 over 17, then can you find the value of the other 5 trig functions of theta, knowing theta is an acute angle? Knowing theta is an acute angle. So for example, using that triangle, then you will see sine theta equals to 15 over 17, right? We get the cosine already. How about tangent theta? That's 15 over 8, right? Secant theta, that's reciprocal of cosine, that's 17 over 8. Cosecant theta, that's reciprocal of sine. And cotangent theta is reciprocal of tangent. That's Mickey Mouse. So nothing hard with that. Nothing hard with that. Okay, nothing hard with that. we will use this later on to solve some basic trigonometry, some triangles, to solve some triangles, some right triangles for a more diverse, not special angles. What I'm about to do right now is to develop or derive the value of trig functions for special angles. Special angles. And that comes from special triangles. There are two special triangles. The first one is isosceles right triangle. To be more precise, that's 45 degrees triangles. Okay. Now, you know from geometry that the sum of the interior angles of a triangle is 180 degrees. So if I have any triangles, it doesn't have to be a right triangle. So let's say this is angle A, this is angle B, and angle C. Then A plus B plus C is 180 degrees. Now that one is something we already know. Now if you have a right triangle, then one of the angle is 90 degrees. That's by definition that you can see again while you read 5.1 later on. So if one side, if one angle is 90 degrees and therefore it's a right triangle, if this is 90 degrees, then the other two must add up to 90. Okay, so the other two must add up to 90. Now, the first special triangles, special right triangles is referring to isosceles right triangle, 45, 45, 90 degrees triangle. Isosceles means that it has two congruent legs. Right triangles means one of the angle is a right angle. Now, the only way that can happen is when you have a 45 degree right triangles. Okay, now 45 degrees right triangles implies that two of the sides are congruent. But we also know from geometry that if two sides are congruent, then the opposite sides, the opposite vertex must be congruent also. Okay, now you will see later on that we can achieve that isosceles right triangle from diagonally dissect a square. Diagonally dissecting a square. Now the second special triangle will be 30 degrees, 60 degrees, 90 degree triangles, or simply 30, 60 degree right triangles. Now the first one, 45 right triangles. 45 degrees, 45 degrees, right triangle. Now it comes from a square that we bisect diagonally. So you start from a square. I think this is a square. Good enough. Too big. Too big. Okay. And then we will dissect that diagonally. Okay. Because it is a square, because you start with a square, when you dissect that, then the angle 90 degrees will be divided by 2, becomes 45 degree each. And because it is a square, then these two sides here must be congruent. This is a right angle, right? Okay, so You can see we actually talk about this triangle here. Oops. No, that's not the sorry. I try to mimic the graph that we have earlier. Here going down. This is right angle. And this is 45 degrees. This is 45 degrees here. This is 45 degrees here. Now, suppose this is the square has side A, then by Pythagorean theorem, you can try by Pythagorean theorem, this will be a square root of 2. Okay, that will be a square root of 2. Now, if your a equals to 1, then the hypotenuse will be simply square root of 2. Why is that? Well, the reason we make it like that because we want to get the trig values of this 45 degrees. So pick either one of 45 degrees. Let's say I pick this is my 45 degrees. Okay, then what is sine 45 degrees? Opposite over hypotenuse, which rationalized to be square root of 2 over 2. You will see that the cosine of 45 degrees will be the same because the adjacent is also 1 with the same hypotenuse square root of 2. While the tangent 45 degrees is 1 over 1, which is simply 1. I need you to memorize this. Okay, the faster the earlier you memorize this, the better you are. The earlier you memorize this, the better you are. Okay, you will see that in trigonometry, you will memorize more formulas than whatever we have learned so far in math. Memorize. The only way you can memorize this, if you have not memorized this before, the only way you can memorize this is by doing it, put it on a flashcard, okay, and keep on staring at that, keep on using it. Okay, that's the best way you can memorize it. Okay, that's for the 45 degrees, 45 degrees triangles. Now, how about the secant, cosecant, cotangent? Well, you can memorize that too, but if I were you, every time I see secant, cosecant, cotangent, I will see that from the reciprocal of cosecant, cosine, reciprocal of sine, and reciprocal of tangent, respectively. So at least memorize these three first, okay? The primary trig functions first. That's for 45 degrees, 45 degrees, and that's how we get the sine, cosine, and tangent of 45 degrees. Part B. 30 degrees, 60 degrees, right triangle. 30, 60, 90 degrees right triangle is actually being developed from equilateral triangle. It is being developed from equilateral triangle. Okay, because it is equilateral triangle, then the length of each sides are congruent, and consequently, because all sides are congruent, then the interior angle will be congruent each one of them, and therefore it will be each 60 degrees. Now, the way we get a right triangle with angles 30, 60, 90 degrees is by bisecting it. Bisecting the vertex angle of that triangle. Okay, so it will be bisected, right? And the angle will also be bisected here. And then you will see this is 90 degrees. Okay. So if I draw the right triangle, it will be approximately like this. Where suppose if this is A, if this part here is A, if this part is A, then the whole part, well, because that A is the dissected one, right? Then this whole part here is 2A. Therefore, this is also 2A. This is also 2A. Then when you use Pythagorean theorem, you will see that this side here will be A square root of 3. And you can try it. You can try it. A squared plus B squared equals to C squared. The A squared is just A squared. B squared is what we're looking for. The C is 2A. And we are trying to solve for P. So P will be 3, I mean A square root of 3. Okay, now notice that this side here, this angle here is still 60 degrees, and this angle here is 30 degrees. If I set my A to be 1, then the hypotenuse will be 2, and the other leg will be just radical 3. Now memorize this picture. Memorize this picture. Trust me. The further you go into math, the more things you need to memorize, and you also need to train more about your photographic memory. Okay, so those who say that photographic memory is a talent, which I think it is, but at the same time, it doesn't mean the talent is not something you can train. Okay, that's something we can train. Okay? Telling me that it's not trainable really refute my experience so far. Okay, I would really like to say that saying that somebody good in math must be smart, somebody smart in math must be smart is actually not really true. At least I don't like to conclude that way. I prefer to say that those who are good in math must be someone who practice a lot. So it takes more discipline, more than just being smart. Okay, of course, if you are smart, you can do things faster, right? Okay, you can do things faster, but even if you are not as smart, okay, but as long as you practice and really try to understand what you practice, it becomes something intuitive for you. Okay, then from here, let's start with finding the value of sine 30 degrees, cosine 30 degrees. Use that triangle, cosine 30 degrees and tangent 30 degrees. And then after that, we would like to do sine 60 degrees, cosine 60 degrees, and tangent 60 degrees. Sine 30 degrees. This is 30 degrees. The opposite is 1 over hypotenuse 2. Right? So sine 30 degrees is 1/2. It's okay? This is 1/2. Cosine 30 degrees, from that 30 degrees, see the adjacent, which is radical 3 over 2. That's the hypotenuse. Tangent 30 degree is 1 over radical 3, which rationalized to be radical 3 over 3. Now, if possible, memorize these two values of tangent 30 degrees. One of them, the original one, and the second one is the rationalized one. Sine 60 degrees, so this is the reference angle, the angle. Okay, then the sine will be opposite of 60 degree is radical 3 over 2. So you're more careful in seeing that now. Cosine 60 degree is 1/2. And tangent 60 degree is radical 3 over 1, or simply radical 3. Now, you need to memorize this. Okay, in fact, let me say one more thing. Things that you don't like, but it's necessary for you. Trig, trigonometry values of special angles needs to be in exact form. For example, later on, when I ask you, for example, cosine 40 degrees. Now, 40 degrees is not a special angle. So cosine 40 degrees, you need to use calculator. But if I ask you what is cosine 30 degrees, because 30 degrees is a special angle, then you need to give me exact value. Okay? If you want to use calculator after that, go ahead. But you start with exact value. Okay? Let me use red color to emphasize that. Now, in the next couple minutes, let's do some problem with this special angle. Suppose, for example, a ladder is put against a wall at 60 degrees angle to the floor. So in this sense, suppose this is our wall and this is the floor. Okay, now the ladder is put against the floor at 60 degrees. Say like this. So this is 60 degrees here. Okay, and of course the wall you expect that to be right angle to the floor, right? Suppose the distance bottom of the ladder. Let's say 7 feet, then find how high the top of the ladder from the floor. So this is the top of the ladder here. This is the top of the ladder. Okay, this is the bottom of the ladder. It says that the distance from the wall to the bottom of the ladder is 7 feet. Then, how high is this? Okay, solution. Of course, you sketch the graph first, and then you say, oh, you know what? Suppose this is my x here. Suppose that's my x. What relates this 60 degrees? What relates this 60 degrees with that x, with that 7? Which function? The tangent, right? Tangent 60 degrees equals to x over 7. Now, because 60 degrees is a special angle, then tangent 60 degree should be given in exact form. Square root of 3. Don't use decimal. Okay, so 7 radical 3 equals to x. That's how you do it. Okay. Now, we will get a break, a little break. You can try to do some problem from, for example, number 12 and number 14. Number 12 and number 14. Let me give you the problems. Number 12 looks like this. This is 3, this is x, this is y, this is 60 degrees. The question is find x and y. Number 14, we have this right triangle here. This is 30 degrees. This is 10, this is x, this is y. And also find x and y. I think each one of them will take you like around only 2 minutes. Okay, together with our break, we will come back at 1:15. Okay, let's start. So here, because it's 60 degree number 12, so what relates 60 degree and 3 and x? Either sine, cosine, tangent. That's opposite over hypotenuse. That's sine. So sine 60 degrees is 3 over x. Now then, sine 60 degree is radical 3 over 2 equals to 3 over x. Cross multiply, x square root of 3 equals to 6. So x equals to 6 over square root of 3. Rationalize the denominator. We get 6 radical 3 over 3. That's 2 radical 3. Okay. Now then, how about the y? What relates 3 and y and 60? It's tangent. Tangent 60 degrees is 3 over y. Tangent 60, as I remember, square root of 3. So y square root of 3 equals to 3, y equals to 3 over square root of 3. I believe that simplifies to be radical 3. Give me a second. Okay, for number 14, what relates 30 degree with x and 10? What trig function? That's a sine, I believe. Sine 30 degrees equals to x over 10. Now, sine 30 degree is 1/2 equals to x over 10. So 1/2 times 10 is 5. Now, how about the y? What relates 30 degrees, the y, and the 10? And that will be cosine, huh? Yeah, cosine. So cosine 30 degrees is y over 10. Now, cosine 30 degrees is radical 3 over 2. So radical 3 over 2 times 10 equals to y. Y equals to 5 radical 3. Now, the thing is, what happened if the angles, not a nice angle like those, not special angles? What if we have not special another angle. So for example, let's say we have the following situation. So I make up numbers, okay? I make up numbers. Suppose I make this 25 degrees here. Okay, and let's say this is x, this is 15, and this is y. So very similar to the last question, but I make it not a special angle. Then we still have the same idea. Then what relates 25 degrees and 15 and x? That would be sine. Sine 25 degrees equals to x over 15, right? Now try to solve for x first. Okay, 15 sine 25 degrees equals to x. And then you use your calculator. Okay, and then we use our calculator. Let me show you. I happen to have graphing calculator though. But you need to take a look on your TI-30 or TI-36. You're not supposed to use graphing calculator. You know, during the test, I saw that most of you use graphing calculator. Not supposed to do. Okay, no wonder you try to cheat using your graphing calculator, and your answers when it comes to graphing is just so off, just so doesn't make sense. You know, okay, it doesn't show the results that's supposed to be. Now, before I go too far, I want to make sure you understand that we are dealing with the angles in degrees. So when you use your calculator, make sure that your mode is in degrees. On my calculator, I go to mode, and I check, oh, my degrees is actually in radian, I need to change that to degree. I need to change that to degree. Okay, it has to be in degree mode. Now, then I can compute 15 times sine 25 only, but the mode is already in degrees. Okay, so when I say sine 25 there, it refers to 25 degrees. Then we say that the answer is, oh, what's that? 6.33927. 6.33927. Okay, now as much as you can, do not compute sine 25 degrees first and round to 5 decimal places and then multiply by 15. Try to avoid that. Let me show you what I was trying to say. Suppose you do it this way. So notice that I don't compute this in decimal then multiply by 15. I actually multiply by 15 right away in the calculator. Now another way to do this is, some people say 15 times sine 25. Sine 25 degrees is 0.42262. 0.42262. If you round it to 5 decimal places and then multiply by 15, what happened? Then from there, you multiply by 15. I will get x equals to 6.3393. Happens to be rounded to 4 decimal places, okay? But the thing is, this part already have rounding error. So this number here will be compounded rounding error. Yeah, we still have rounding error here. Okay, we still have rounding error there, but we can tell that when we plug in 15 times sine 25 degrees in our calculator will see this sine 25 degrees up to like around 9 or 10 decimal places. Okay, so what happened here, you already rounded, then you use a rounded number to multiply by 15. Okay, so it becomes a compounded rounding error. Okay, while in the previous situation here, we have compounded rounding error, but the rounding is so small because we used the numbers from calculator. Okay, now as much as possible, try to avoid doing that thing. Okay, try to avoid that thing. Will you penalize Thomas if you see that? I may, but even though I don't have interest in penalize too much, maybe like just half point, you know, maybe just half point if you make mistake by rounding too early, okay, using calculator too early, then that will be the case. Okay, that's for to compute sine 25 degrees and how do we use that in our calculator. Now, let me give you suggested homework first from this 5.2. The suggested homework from 5.2 will be number 1 to number 33. 1 to number 33. Yeah, including the word problems whenever possible. Okay, including the word problems whenever possible. We have identities on the later part of that section. Okay, so let me call that part A. But I will go over the identities tomorrow. Yeah, today, let me go back to 5.1 because I want to give you foundation, right? This is the very required foundation, basically day one foundation for your trigonometry. Now tomorrow you will see that's a lot heavier. It will be a lot heavier. it will be even worse if you don't study from what we do today. Now, stop playing catch up though. Stop playing catching up. Okay, no. You dare enough to take 5 units in 6-week class, and that's pre-calculus, then you know you will study hard, right? Telling me that you don't have time to study, of course, it's an excuse, but whatever excuse you have, it will not help you. In the end, it's about how well you perform in the test, in your final, right? Okay, so no, excuses will not help you. Okay, you need to manage your time very, very well. Now, I go back to the material from 5.1, the one that I will need you to read. 5.1, some definition of angles. The first one, acute angle. A theta is acute angle if the theta is between 0 degrees to 90 degrees. Obtuse angle if the theta is more than 90 degrees but less than 180 degrees. Two angles are complementary. Angles A and B are complementary if the sum is 90 degrees. Yeah, you need to remember those terminologies though. Okay, and angles A and B are supplementary if the sum is 180 degrees. Now pictorially, two angles are complementary angles if those two angles add up to a right angle. So let's say this is angle A and this is angle B. Then this is supplementary. I'm sorry, complementary. And two angles are complementary and supplementary. Two angles are supplementary if the sum of those two angles is 180 degrees. Basically what happened is it will give you, let's say this is angle A and this is angle B. They will add up to 180 degrees, which is a straight line. Okay, that's for obtuse angle, acute angle, complementary angle, and supplementary angle. Definition 5. An angle is in standard position if the vertex is origin, the initial side is positive x-axis, and measured counterclockwise. So suppose I have a rectangular coordinate system here, okay, and then I have an angle like this. Now then this alpha, let's call this alpha here, then this angle is angle in standard position because it starts from, it is being measured from positive x-axis with vertex at origin going counterclockwise. Okay, going counterclockwise to the terminal angle. Okay, now here's a note. Here's a note. Unless otherwise stated, an angle in coordinate system is in standard position. I'm sorry, I wrote something wrong up here. It's supposed to be terminal side. Okay, so this is what we call the terminal side. This is terminal, and this is initial. So the inertial side is positive x-axis going counterclockwise to the terminal side. Okay. How about coterminal angle? Coterminal angle. Coterminal angles. Two angles are coterminal if they have the same vertex, the same initial side, and the same terminal side. So let's see this way. Suppose this is my positive x-axis here. And I have the terminal side here. Okay, now then, this angle, call that alpha, for example, that angle is coterminal, coterminal angles to this angle here. Let's call that angle beta. Give me a second. So you see that they have the same vertex, the same initial side, and they have the same terminal side. It is just that beta is actually go one more round than alpha, such that suppose let alpha be, let's say 70 degrees, then beta will be in this case, from the picture, you see 70 degrees plus 360 degrees. Right? Okay. Now, in fact, we may have negative angle. We may have negative angle. That is if we start from the positive x-axis, but we go clockwise instead. If we go clockwise instead, let's call that angle gamma. Now, if we go clockwise instead, you see we still have the same vertex, we still have the same initial side and in the same terminal side. It's just the direction is the opposite direction. Now then, we say this angle gamma here will be angle 70 degrees minus 360 degrees. Angle 70 degrees minus 360 degrees, that's angle negative 290 degrees. Okay. Now, these three angles here are coterminal, and therefore we may use the following notation. If these two angles are coterminal, we use this notation here. So you can see there are actually zillions angles that coterminal to each other. Just keep on adding 360 degrees or subtracting 360 degrees. Okay. Next, 7. DMS style. DMS angle. That stands for degree, minute, seconds. Angles. That's because of the following. Now, we usually just write it in degrees with decimals, but we can also break it up further into minutes and seconds, where 1 degree is equal to 60 minutes, which is written 60 minutes, like that. And 1 minute is equal to 60 seconds. Just like the way we do our clock. So instead of making it into decimal, we break them up into degree, minutes, second. Suppose, for example, what we do here is mainly arithmetic though. Suppose, for example, we have 29.72 degrees. Write that in the MS form. Degree, minutes, seconds. The degrees there, the 29 degrees, right? The 29.72 degrees. That's actually 29 degrees plus 0.72 degrees. Is okay? Now, we will change this decimal part of the degrees into minutes by multiplying it by 60 minutes. So 0.72 times 60 minutes. Okay, so that will be 29 degrees plus 7.2 times 6. plus 43.2 minutes. Now, I don't like that decimal in that minutes there. I break it further. This is 21 degrees plus 43 minutes plus 0.2 minutes. Now, that's the one I multiply by 60 seconds. So that will be 29 degrees plus 43 minutes plus 12 seconds, which we will write as 29 degrees with a plus sign, 43 minutes, 12 seconds. Okay, now you actually see that we usually have the decimal method. Decimal means one digit for 10 numbers, right? And this DMS form is actually called hexadecimal. Means for you to go to the next digit, there are 60 units there. And then for you to go to the next digit, from degree to minutes, 60 digits, 60 numbers. Between minutes, 1 minute to seconds, there are 60 seconds. Like that. Now, suppose, on the other hand, we go backward. Suppose I have 57 degrees, 34 minutes, and 51 seconds. Then what will this be in decimal? In degree only, which means it is a degree with decimals. We will do the following. We do it from the last part, 57 degrees, 34 minutes, 51 seconds equals to 57 degrees, 34 minutes plus 51 over 60. But when you divide that seconds by 60, you will get minutes. Okay, 51 over 60 give me 0.85. So this will be 58 degrees, 34 minutes plus 0.85 minutes. Now put things together. This is 58 degrees plus 34.85 minutes. Now change it further to degrees. 58 degrees plus 34.85 divided by 60 minutes give you degrees. I get 58 degrees plus 0.58083 bar degrees. Now, we usually just round it to 5 decimal places, right? Okay, so I get, oh, they happen to be nice numbers. So 58.58083 degrees. That's how we convert from DMS to degree, and the previous one from degree to DMS. Okay. Now the last part for this is it. For today's lecture. I don't finish this though. This is 5.1, but I don't finish this. This is basically what I can. I need you to study well from your 5.1. Part 8, radian measure. You need to be good with radian measure starting Wednesday. Starting Wednesday, you need to be good with radian measure. Today, I just give you the small introduction. Now, here's what happened. Beside degree measure, we also can measure an angle using radian measure, but the idea is as the following. The idea is as the following. Okay, let's say you have a circle. Okay, I purposely put a coordinate system there, but the idea is the following. Radian measure is maybe I define 1 radian first. 1 radian is the angle. 1 radian is the angle such that the ratio of the arc subtended by of that arc there with the correspond to that angle, and the radius is 1. So let's call this the center O, and this is P, this is Q. Okay, so 1 radian is defined to be the central angle that's the central angle such that the length of PQ, the arc PQ, is equal to the radius. That's 1 radian. Okay, the length of PQ is equal to radius. Okay, then if you have that situation in a circle, then this angle here is what we call 1 radian. Okay, that's the definition of 1 radian. Now, the further definition, it's too far now. Further definition, suppose I have, suppose I have a circle. Okay, is this circle? Okay, and then I want to get the radian measure of, let's say, this angle. Okay, let's say this is theta. Okay, now theta in radian, is equal to the ratio of the arc PQ, the length of arc PQ over the radius. Okay, now we usually call that S for the arc length. Let me change that. The length S. Okay, so if this is the arc length formed by central angle theta divided by the radius, that ratio is theta in radian. That ratio is theta in radian. Now, that's another way to look at the definition of angle theta in radian. Now, let me derive the relationship between theta in radian and theta in degree. Now, notice that theta 360 degrees corresponds to one full circle, one cycle, right? Now, the circumference of the circle of one full circle is 2 pi r. Okay? Now, so what is theta in radian? That will be the arc length 2 pi r over the radius r. So one cycle theta in radian will be 2 pi. Now, radian measure is without degree sign, without any sign actually. It becomes unitless because it's length divided by length, whatever the units, you know, as long as they are the same units, they will cancel, right? So you see that one cycle, the radian measure is 2 pi. That corresponds to 360 degrees. Therefore, if I divide by 2 both sides, pi radian is 180 degrees. Now you see one of them with degree sign, the other one without any sign. So if you have an angle without degree sign, it must be in radian. Maybe I write it down. An angle without degree sign must be in radian. Keep that in mind. Okay. Now, let's go back to that circle. Okay, now then you see that if the angle is 180 degrees, okay, 180 degrees, maybe I put it here instead. If the angle is 180 degrees, that's equivalent to pi radian. Now try to visualize this though. 180 degrees is pi radian. Now if I divide that by 2, I will get 90 degrees. Oops. I will get 90 degrees. But that 90 degrees corresponds to pi over 2 radian. 45 degrees is half of that 90 degrees. 45 degrees is half of that 90 degrees. Degrees. Now that corresponds to pi over 4. Now try to picture that though. The key is 180 degrees pi. So when you divide by 2, that's 90 degrees. Divide by another 2, that's 45 degrees. So that's pi over 4. Now 60 degrees is 180 divided by 3. Degrees is 180 degrees divided by 3. 60 degrees is 180 divided by 3, so that's pi over 3. And finally, 30 degrees is 180 degrees divided by 6. So 30 degrees corresponds to pi over 6. Now, I need you to memorize this for now. Of course, 0 degrees is just 0 radian. Okay, 30 degrees is pi over 6 radian. Okay, for now, this is what you remember. Tomorrow, we will start working on problems from 5.1. I am to the point that for 5.1 material, read the book and then read these notes. Read these notes first from 5.1. Okay, read these notes first from 5.1, and then tomorrow we go on more on 5.1, go back to 5.2, finish up 5.3. Okay, on Wednesday, I think we will be able to do 5.4 and 5.5. Okay, that's for today then.